Okay, so good afternoon and welcome back to the weekly live tutorial sessions on ME67 wheel mobile robots. So we'll be discussing in this session, we'll basically cover the summary of the topics that has been covered for week 6 lectures. And for the second half of this session, we'll also cover some sample tutorial problems that may help those who are taking the courses to solve the weekly assignment quizzes. So as you can see, on week 6, our main topic, the key topic of interest was mobile robot navigation. And actually, we have we in the previous couple of weeks we have actually covered the topics of perception on week 4. This is what we covered on week 4. And on week 5 we have covered topics such as the error propagation, localization, and simultaneous localization and mapping. We have covered this on week 5. And for week 6, we will be covering topics regarding, that is this week 6 will be mostly on navigation. So based on what the robots perceive, like using the sensors, it will basically create a model of its own environment. And using the information from what it has perceived and from whatever it has learned from its odometry, fusing all these together, the robot will be able to localize itself on a map. It could be provided with a map, or it could simultaneously create a map as it is localizing also. So either ways, as of now, until now we have actually covered all the topics up until here, because the robot can at this time the robot can actually localize itself uh, on a given map, or a map that it has created on its own. And once it has once it is fully aware of its position on a map, what it further requires is that, like, it also has been given a command to go to a goal position. So once it knows its relative position on a map, what are the further course of action a robot has to take so that it can reach or attain a goal position? So those topics comes under navigation, right? So like once the robot has localized its own position, what are the course of action the robot should be taking in order for it to reach the final end position? Because like as you can see, the workspace of a robot is unrestricted or unregulated. And if it is starting from a start position, and if there is a goal position, and if the robot knows its whereabouts within a given map, where it knows its own position, there could be multiple ways that it could start from a start position and reach all the way to goal position. Then how do we select the most appropriate path? Like there could be some sort of an optimization criteria. You could choose the best path based on the shortest distance it covers. You could also select a path that gets to the goal position in shortest time. And maybe you could also you could also have an optimization criteria based on the path which consumes the least amount of energy. So all these, whichever is your priority, or you could have a weighted average of all these objectives in order for you to reach the goal position. And once you have decided on the path, like once you have decided on what path to take, then you will have to your controller will have to give the right commands to the actuators, so that the actuators will take the robot from its current position to the goal position. So that is where this stage comes along, motion control, right? This comes after path planning. We'll go straight into motion control. And all these processes, we can actually call this under an umbrella term called navigation, right? To decide or to choose an optimal path, and then further to give the right course of control inputs to the actuator, so that it will basically take the robot from its current position to the final goal position. So basically, what navigation means is that, like, given partial knowledge, about its environment and a goal position or a series of positions. A navigation encompasses the ability of a robot to act based on its knowledge and sensor values so as to reach its goal position as efficiently and reliably as possible. It's a lengthy sentence, but this is what more or less captures the idea that we have just discussed. So, like if the robot knows its position, if it wants to go from its start position to a goal position, basically navigation covers the navigation basically covers all the course of actions that takes the robot from the start position to the goal position uh, in in a way that is efficient as well as reliable as reliable as possible. So that is what we deal on navigation, essentially the topics for week 6. And yeah, what are the sub classes or the subdivisions in navigation? So there are two objectives that navigation will have to satisfy. So the one of them is path planning. So like just like what I have said earlier, like there could be multiple possible paths that a robot could take from a start position to an end position. Then how do we choose the optimal path? So that is what this problem deals with, path planning. It says identifying a trajectory that will cause the robot to reach the goal location when executed. So path planning algorithm deals with choosing the most appropriate algorithm or most efficient and reliable algorithm that will take the robot from its start position to its final end position. And the second important objective of path planning algorithms are to avoid obstacles, right? So it says given real-time sensor readings, modulating the trajectory of the robot in order to avoid collisions. So maybe if the obstacles are dynamic, like when the robot was doing its localization and map building, but during that time there may not be any obstacles. Since you could assume the obstacles could be dynamic, it could be changing its location as a function of time. So as the robot is moving through its planned trajectory, the sensors may sense some obstacles or some foreign objects. So the navigation should also deal with modulating the planned trajectory so that the robot will get to the goal position safely without colliding or interfering with any obstacles. So these are the two objectives of path navigation. One is for path planning, and the other is for obstacle avoidance. And for all the algorithms that we have discussed in the week, there are assumptions that we have made. One of the assumption is the robot is holonomic. So, like if you can recall from week 2 lectures, a holonomic robot is if the total number of controllable degree of freedom is equal to the total number of degree of freedom, right? So it can be confusing, but total number of degrees of freedom for a wheel mobile robot is actually 3, right? Because a wheel mobile robot basically moves in a plane. So a plane has any rigid body on a plane has 3 degrees of freedom, right? 2 translations, maybe along x and y axis, and 1 rotation about a perpendicular z axis. So that is the total degrees of freedom. Total degrees of freedom. But if a mobile robot has controllable degrees of freedom that is equal to the total degrees of freedom, then that robot can be classified as holonomic robot. For example, if you consider a differential robot, you can only have 2 controllable degrees of freedom, right? 1 motor for each field. So that is less than 3. So that does not make it holonomic. Whereas in the case of maybe a omni-wheel drive, it has three control inputs actually. So again, that makes it holonomic because that is equal to the total degrees of freedom of a plane, the space in plane. Sorry, of a plane. So those are the two assumptions. The robot is holonomic, and the second assumption is a robot is simply a point. So earlier, until all the topics that we have discussed so far, we treated robot as a rigid body with a finite volume or a finite area of cross section. But for path planning, we would treat a robot as a point, and then we would compensate this thing by inflating the size of the objects. For example, if you have an obstacle like this, and if you have a robot like this, you can get an equivalent effect by treating the robot as a point and inflating the object with an offset that is comparable with the radius or the dimensions of the robot. So like if you can see, when the robot is actually interacting or just colliding with this object, this is as same as this point, coming into this field, this inflated field. You can treat, you will more or less get the same effect. And the advantage is that the second approach where treating the robot as a point would be much more easier, and treating a robot as a point and inflating the obstacles to compensate for such an operation would be far more easier than doing it this other way, doing it this way, right? Because you don't have, say you consider a robot as a holonomic robot, so the orientation does not really matter actually. So in that regard, you can always treat it as a point. Okay, so moving on. Uh, in the earlier part of this lectures, we have discussed various methods of path planning, right? So as I've said earlier, there were two objectives of navigation. One was path planning, and the second was obstacle avoidance. And maybe the first out of, I believe we had 4 lectures or something, and 3 lectures were dedicated for discussing various path planning methods. So we'll also, for the purposes of this session, I'll basically cover a brief summary of various path planning methods. So again, path planning method basically has two subsections. So one is a graph construction, and the other is called a graph search. So we still haven't defined what each of these are. So basically, path planning methods, we call it as graph search method. So in graph search theory, a connectivity graph in free space is constructed and then searched. So like, for example, if you have a space, or if you model your environment, robot's environment as such, it may be riddled with multiple obstacles. And since we have already covered localization, the robot will start from a start position. This, you can call it as a start position. And the robot may also have a goal position, a target position. So what this graph search method does it basically module it basically makes it out of this given environment, it actually creates a connectivity graph. Connectivity graph in the sense, each and every node of these obstacles are taken into account, or maybe some other features of within this map is used to construct a connectivity graph, right? And yeah, a connectivity graph is first created, and once you have this connectivity graph, the second process is called graph search, where a most optimal path along this connectivity graph is searched. Most optimal path to reach from a start position to a goal position will be searched. So that is what will first a connectivity graph will have to be constructed. Then it will have to be searched for an optimal path. So this can be done in 2 ways. One is called graph construction, where the nodes are placed and connected via edges. So it'll be riddled with multiple nodes, and each of these nodes will be connected by edges. How do we create this graph? We'll come across that in a few minutes. And then the second process would be, like, once we do the graph search, the second option would be graph search, which deals with the computation of optimal solution. Right. So once you create a connectivity graph, the next procedure is to find or compute the optimal path through this graph. So again, like once you are through with this, there are multiple ways you could create this connectivity graph. So under graph construction, it basically is a creation of a connectivity graph in free space. And there are multiple methods where you can do this graph construction. So those are, if you can recall from the lectures, one of them is called visibility graph. The second is called Voronoi diagram, and the third is called the cell decomposition methods. And there are two different kinds of cell decomposition methods. We'll see that in the upcoming slides. So we'll go in detail about each of these construction methods. So the first would be graph visibility graph, where the defining or yeah the defining feature of a graph construction method is the robot's path would basically come as close as possible to the obstacles. So this may have advantages and disadvantages. So one of the advantages is that, like, since the robot is not really afraid to come as close as possible to the obstacles, it can more often lead to the shortest path, shortest distance path. Right, as the robot is free to move as close as possible to the obstacles, it can actually end up with the shortest path solutions. It can easily find shortest path solution if that is your priority. And another example is that, like, if there are some sort of errors, like if the errors have not been properly addressed, maybe if there are noise from the sensors, or if there are errors from the encoders, or if your wheels are slipping, and if you haven't properly compensated that, then there is a high chance of collision with the obstacles, right? That could be one of the disadvantage of visibility graph. And the second method of graph construction would be Voronoi diagram. So this is exactly opposite to visibility graph. Here, the path of the robot stays as far as possible from the obstacles. So for example, if there are two walls like this, the robot will stay as far as possible from these two walls. So if the robot is like this, its trajectory would be somewhere in between. The perpendicular distance from the trajectory to either of these walls will be equal. It will try to go somewhere in the middle of these two walls. So that is the defining feature of Voronoi diagram. And the third one would be cell decomposition method. So where what it does is that it will basically discretize the grid into multiple cells, and whether or if it will also detect whether or not an obstacle is present on a cell. And if an obstacle is present on a cell, it cannot go through that cell. If it is free from obstacles, it can go through a free cell. So that is the basic principle of cell decomposition methods. So we'll cover this in detail. Yeah, so this is what visibility graph is all about. So we have a start position over here, and we also have a goal position right at here. And what you see as these polygons are obstacles. These are depiction of obstacles over here. So yeah, what does the basic concept of visibility graph is that the visibility graph of a polygonal configuration space consists of edges joining all pairs of vertices that can see each other, including both initial and goal positions, as well as vertices. So what does this mean? Joining all pairs of vertices that can see each other. So for example, if you take a look at this vertex, it can the vertices that is directly on its line of sight are, this vertex is directly on its line of sight. This vertex is also directly on its line of sight. This is also another vertex. Then what else are there? This vertex is also on its line of sight. This vertex is also directly on its line of sight. And what about this vertex? That is not on its line of sight because it has to go through this obstacle, right? So that is what it means by the objects that vertices that can see each other. One more example, like if you start from the start position, what are the vertices that the start position can see? So one of them would be this vertex, another one would be this vertex, another one would be this vertex. So in visibility graph, each and every vertex will basically create an edge to all the other vertex that it can see. So it goes on for each and every vertex. Then all these unobstructed lines. The procedure is, the unobstructed lines, or we can call these as roads. A network of roads. So these unobstructed straight lines joining those vertices are obviously the shortest distance between them. Like for example, if this is one vertex and this is another vertex, if you consider this to be an unobstructed line, obviously this should be the shortest distance between this vertex and this vertex, right? And the task of the path planner is to thus find the shortest path from the initial position to the goal position along the roads defined by the visibility graph. So what this visibility graph does is it will only create a network of roads. That's all it does. And on later, when we comes to path planning, the path planner will have to select the most appropriate path. So technically, it can basically reach from the start position. It can take any roads. Actually, it can go like this. It can go like this. It can go however it wants, zigzag manner. So depending on the criteria, maybe our criteria could be to take the shortest distance. That may not be the case all the time, but for example, like if our priority is to reach from the start position to the goal position, such that it takes the shortest distance, then as you can see, a path through this is obviously the shortest distance, right? This path. That will be the shortest distance from the start position to the goal position. And again, like just like we have discussed in the previous slide, as you can see, the robot is actually almost touching these obstacles. It can go as near as possible to an obstacle. It's not shy to take maybe to go as far away from this obstacle. It can easily go as close as possible as it wants. So inherently, it will also yield to like since it is not shying away to get as close as possible to the obstacles. Inherently, it can also yield to the shortest length solutions, right? So that is these are the features of visibility graph. That is one of the graph construction method. And the second would be a Voronoi diagram. So again, the concept is for each point in free space, its distance to the nearest obstacle is computed. Like for example, like if there are two obstacles like this is one obstacle and this is another obstacle. If over here is the position of a robot, I'm depicting this by a square. You can actually compute the distance between the nearest obstacles, right? Using the sensors that you have, like the robot will have its ultrasonic sensors, whatever sensors it can use to find the distance to this obstacles. Okay, so what next? At points that are equidistant from two or more obstacles, such a distance point has sharp ridges. So, like when the robot at a point which is equidistant from these two obstacles. So, consider for example, if over here is the robot and it is by default at an equidistant at an equal distance from this obstacle, maybe obstacle 1 and this will be obstacle 2. The map basically create a ridge in the sense like a valley kind of a thing. So in Voronoi diagram basically consists of edges formed by these sharp points. So whatever ridges that you see on a Voronoi diagram, these are basically equidistant from all the objects that you see. Maybe this line is basically equidistant from these two walls. And this line is equidistant from these two corners of this obstacle. And what else can you say? Maybe this line could be the equidistant from this and this. And all these curves, whatever you see here as curves are basically equidistant points between a corner and a line, right? For example, if you have something like this, if you consider this to be a wall and this to be a side of an obstacle, so when the robot is starting from here, it will actually go along a path that is equidistant from this obstacle and this wall. And once it reaches the corner, or once it reaches to the proximity of a corner, it will basically curve. Because the curve is basically the area where the shortest distance between a wall and maybe a straight line and maybe a corner. And then it basically curves down, things like that. So wherever you see this corner, that is basically where you see the robot interaction between a corner and a straight line. And for example, here also you can see a curve. So that is basically a point that is equidistant. Those curves are basically equidistant from these two vertices. And here also you may see a curve because that could be equidistant from this corner and this line. And here also you can see a small curve, maybe a parabolic curve that is equidistant from this line and this corner. Okay, so one more feature. Since this path planning algorithm maximizes the distance between the robot and the objects in the environment, any short range sensor on the robot will be in danger of failing to sense its surroundings. So this could be a massive drawback of Voronoi a path planning using Voronoi diagram. So, for example, if the distance between these two obstacles are actually too large, and the robot is somewhere in between these two obstacles, and if its sensors are not powerful enough to detect these edges, maybe it's using short range sensors, then it may not be able to detect the edges, and hence it may not be able to even create this roadmap at all, because the sensors are short range, and it may not be able to detect the edges if the obstacles are too far away. So that could be a potential pitfall of graph construction using Voronoi diagram. And yeah, the third one would be what we call as cell decomposition method. And there are two different kinds of cell decomposition methods. So one of them is what we call as exact cell decomposition, right? So it basically at these vertices, it basically divides this entire configuration space into multiple cells, depending on and it will also be a function of the vertices of all the obstacles, right? So boundary of the cells is based on geometric criticality. The resulting cells are either completely free or completely occupied. So this cell one is actually basically completely free, but as you can see, this cell two, it may not be completely free. This is cell 7, this is cell 3, and all the intermediate cells, it could be fully occupied. And there are cells that could be completely free. So the basic abstraction behind such decomposition is that the particular position of a robot within each cell of free space does not matter. So in this case, the position of the robot, where the robot is within this particular cell, is not really a matter of concern. As long as the robot is within this cell, that is acceptable. It does not matter whether the robot is here, here, or here, or here. Does not matter. But the only requirement is the robot should be somewhere within a cell, right? So another thing is that the key disadvantage of exact cell decomposition is that the number of cells and therefore the overall computational planning efficiency depends on the density and complexity of these objects in the environment. So for example, if there are a few obstacles in the space, the number of cells would be too few. And if the number of cells is too few, the resolution will also decrease as a result. So the probability of finding a robot at a given position would be, as a consequence, will be very low. So if you have multiple number of obstacles with multiple edges, then you may get even more resolution because there are obviously more vertices involved, and as a result, you can have more number of cells, and as a result, that may also increase the number of that also increases the resolution of this configuration space. And as a result, you will be able to locate the robot with a higher resolution. So again, this method is as it's dependent on the number of cells. Sorry, since it is dependent on the density and the complexity of objects around the environment, its resolution can also be influenced. And as a result, you cannot call it to be very robust. because the probability that it can be at a given location can be either high or low depending upon the density of the objects in its environment. And yeah, there is one more thing called approximate cell decomposition. So what it does is that the procedure is to discretize the grid into multiple number of grids, right? So the world is tessellated or discretized, transforming the coordinates, transforming the continuous real environment into discrete approximation of the map, which depicts what happens to the obstacles, filled and free areas with this transformation. So another thing is like if you take a look at this obstacle, uh, it only partially fills a cell. Some cells it fully occupies, and if you take a look at this edges, some of the cells are partially filled. Some of them are partially filled, some of them are fully filled, some of them are partially filled. But when you discretize the grid, you cannot have a when you discretize it, you cannot have a partially filled or fully filled condition. So you can only have either it is filled or you know it is not filled. You cannot have something in between. So as a result, when once you translate or once you transform all the obstacles into this space, it will get tessellated or it will get pixelated, as you can see. All the obstacles here gets somewhat pixelated. And as a result, you may also lose some of its features. As a result, see here you have a corner, but you have lost that feature because whatever you are seeing here is not very well defined. So, like as a consequence, what are the consequences of this? Like it is possible for narrow passageways to be lost during such transformation. Like for example, in the actual case, you have a narrow passageway, but due to the fact that you are discretizing it and you cannot have partially filled or maybe a three-fourth filled cell, you can only have either fully filled or partially filled. So as a result, once you translate this graph onto an approximate cell decomposition, this gap or this feature over here was lost here. So this narrow passageway here was lost. So ideally your robot could have gone like this, but due to this inherent nature of this exact approximate cell decomposition, it cannot go like this because it thinks there is an obstacle here. So it will have to go for alternate paths that may be less efficient or less far more less of efficient than going straight like this. So yeah, that could be a potential flaw of approximate cell decomposition. Yeah, so we have basically covered different methods of graph construction. Right, these are all different methods of graph construction. The first one was visibility graph. Second one was Voronoi diagram. And on the previous slide, we have covered exact cell decomposition. We have also covered on this current slide approximate cell decomposition. We have also seen what are the advantages and disadvantages of all of these different methods of graph construction. So in navigation, once you do this graph construction, the next procedure is to select the most appropriate path. Like we at the moment, like we can have multiple solutions, multiple paths are possible. But out of all these available paths, how do we select the most appropriate or most efficient path? So that is where the second phase comes. We call this as graph search. And all the algorithms that we discuss in graph search deals with selecting the most efficient or most optimized, or you can even call it as the best path out of all the paths available. So what are the key steps in graph search? We'll go this one by one. So the first step, earlier in graph construction, like what we have covered in the previous slides, earlier in graph construction, the environment map has been converted into connectivity graph. We have done that. So whatever map representation is chosen, the goal of the path planning is to find the best path. It says the best path in the map's connectivity graph between the start and end goal. So whatever we have obtained from graph construction, The graph search objective is to find the best path, the best path. And point three states here the keyword is best. And what does this best mean? Because it's a general term, it does not mean a single thing. It can mean the best path may of your preferred optimization criteria. It could be the shortest, the path which has shortest distance. It could mean the path which has shortest time. It could mean the path that has shortest travel cost, or it could even be a combination of all of these three things. And if you prefer to give more weightage to shortest time, you can add more weight to the shortest time. Or if your priority is shortest path, you can add more priority to shortest path. So the best may not mean a singular criteria. It can mean any of these criteria, depending on this application or depending on the designer's preference. And if you are considering the shortest travel cost, the travel cost is actually defined by this formula. This is which each of these term is defined as f of n is actually expected cost. For example, if a robot is moving from one cell or from one position to the another cell, what would be the cost of travel? So the total expected cost would be sum of path cost and sum of heuristic cost. So like basically we will try to cover, we'll give a more detailed explanation of what these path costs are and what these heuristic costs are. And we'll also cover, different graph searching algorithms that can have different behaviors of path costs and, heuristic costs. And just by simply adding this path cost and heuristic cost, you will get the total expected cost. So if you sticking on the same topic of graph search, there are multiple algorithms. So the first algorithm, yeah, there are two different ways to which you can actually explore all these paths. So the first one is actually called breadth first graph search algorithm, and the second is called, the depth first graph search algorithm. So for example, I will give you one example. In breadth first, if you have a start position and there are multiple nodes like this, like you essentially have a connectivity graph from uh, from the graph construction phase. 1, 2, 3, maybe you can have 4, 5, 6, 7, 8. And then you will have a goal position here. So in breadth first, the principle of breadth first is that it begins at the start node and explores all its possible nodes. So it starts from the start node and it explores its neighboring nodes. So what are the neighboring nodes of the start node? Neighboring nodes means the nodes that are adjacent to the node that we are investigating. So the nodes that we are investigating are 1, 2, and 3. So we'll begin with start and we'll investigate on 1, 2, and 3. Right? Then what we do? Then for each of these nodes, its neighboring, it explores all of their unexplored neighbors and so on until it reaches its goal position. So from start, we have actually explored nodes 1, 2, and 3. Then on the next step, then what are the neighboring nodes of 1? Unexplored neighboring nodes of 1. So in this case, the unexplored neighboring node of 1 is just 4 because there aren't any more nodes that is adjacent to neighboring node 1. So 4 comes the next path. I'll use the same color. Yeah, 4. Then what about the other? Then what about 2? We have already explored 2. Then what are the adjacent nodes of 2? That will be 6 and 7. 6 and 7. Then again, what will be the neighboring nodes of 3? That will be just 8. Because there are no other adjacent nodes connected to node 3. We'll stick with 8. Okay, now we'll go with here we have actually explored S start node, we have explored first node, we have explored third, first, second, third, we have explored fourth, we have explored sixth, we have explored seven, we have explored eight as well. Now again going back to fourth node, what are its neighboring nodes? The neighboring nodes is just five, and we'll go to five, node five, right? Okay, then we'll actually go back to node 6. What are its unexplored nodes? Nothing has been unexplored, everything has been explored. Then we'll go to node 7. What are its unexplored nodes? The only unexplored node would be the goal position. So this will be the goal position. So this is how this graph search algorithm explores. So like it will propagate from a start node to this end node using the breadth search algorithm, because it will first explore all the neighboring nodes. Then it will explore the neighboring nodes of corresponding nodes, right? It will basically go like a wildfire, breadth wise. That is what this breadth first algorithm does. And what what about depth first? So again, in case of depth first, if I reproduce this connectivity graph, then 5, then from 2 we have 6 and 7, then from 3 we have 8, then from 7 we have this goal position. So what it is that, like, unlike the breadth first algorithm, it expands each node to its deepest level of the graph until the node has no more successors. So for example, if you begin from the first node, the start node, it'll go to the deepest level. Maybe it'll go to this level, one from S to 1, then 1 to 4, then 4 to 5, S1, 1 to 4, 4 to 5. Then from 5, it cannot go anywhere because there is nothing connected to 5. Then what does it do? The search then backtracks by expanding the next neighboring node of the start node until its deepest level reach, and so on. So the drawback is that it may visit previously visited nodes. So for example, we have taken this path from start to 1 to 4 to 5. Then from 5, since it has nowhere to go, it will backtrack to 4. So can 4 be expanded depth-wise? No, because there is nothing unexplored on 4. Then it will again backtrack to 1. And 1 also does not have anything. It cannot have anything to, it does not have any more further adjacent nodes that it can be expanded depth-wise. Then again, it will go back to S. Now again, it will try to go depth-wise on another path. Maybe if you take this path, it will go to 2, then it will go to 6. Right? So the next path would be 2 and 6. Right? So then 6 does not have any more further paths. It does not really have any more nodes connected to it. So it will backtrack to 2. Then can it further extend from 2? Does it have any more further node connected to 2? Yes, it has 7, and 7 is connected to goal position. Then from 6, it will backtrack to 2, then it will go to 7, then it will go to the goal position. Right? And it does not even need to consider this because it has already reached the goal position. Right? So like despite the fact that it can revisit the previous nodes, like once it has reached a dead end, it will backtrack, it will go through another node, and again it will backtrack, and it will come back, it will go to another node. So like it has a problem of backtracking, but despite this, sometimes it may be even more faster, or it may be much more beneficial than breadth first, because as you can see, this part of node need not be even considered. And without even being considered, it actually reached the goal position. Actually. So yeah, those are the different philosophies of graph searching algorithms, starting from start position to this end position. Right. So there are a few examples of each of these algorithms. So One of the prominent breadth first algorithm is what we call as a graph search algorithm. So like for example, in graph search algorithm, if you can recall from the previous slide, the expected cost is sum of the path cost g of n plus some scalar multiplied by this heuristic cost. So in graph search algorithm, we don't have this, we don't consider this heuristic cost. We'll come to, we'll discuss about what this heuristic cost means uh, on the later slides. So in case of Grassfire breadth first algorithm, we only consider this path cost. So what does this path cost imply? So for example, if the robot is starting from a start position, the cost for it to take to move from its current position to the next position is what you call as the cost position. For example, it can only move 1 unit from here. The cost would be, you can consider it to be 1. So for all the blocks that is 1 unit away from the start position, it will have a cost of 1. And if the block is actually 2 units away from the start position, it will have a cost of 2. For example, this block is actually 2 units from the start position. So all the blocks that is 2 units from the start position will have a cost of 2. And what about this block? That is also 2 units. 1 unit here, 1 unit, 1 unit towards right, 1 unit towards top. So this is also 2 units. And what about this block? This is also 2 units. One to your left and one to the top. That will be 2 units. And this is also 2 units, 2 units. And what about this? This will be 3 units. 1 unit down and 2 units to the left, or 2 units to the left and 1 unit to the down. So similarly, just like a graph fire, it will propagate from a start node all the way to the final goal position, where it will have uh, its own assigned cost, total expected cost. And the most appropriate path would be the uh, path along the shortest, the path which yield the shortest expected cost. So like it does not mean it has to be a single path. There could be multiple paths. For example, this is one path starting from here, from the start position. It can go like this: 1, 2, 3, 4, 4, 5, 6, 7, 8, 9. It can take this path. It can also take this path: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It can take this path. It can also take this path: 6, 7, 8, 9, 10. So yeah, multiple paths can be realized for it to reach from start position to goal position. That gives you the least expected cost. What about this path? 0, 1, 2, 3. Again, it will go 2, 3, 4, 5, 6. No, it's not optimal, right? Because it will only increase the further cost. So path along this or this or this path will yield you the path which has least expected cost. This is also another potential path. It can also go like this. So that is breadth first Grassfire algorithm. And the second would be similar to a breadth first algorithm, but in this case, the path cost is not constant. For example, if I'm again recalling f of n as g of n times epsilon h of n. So in case of Dijkstra algorithm, this heuristic cost is again 0, but this g of n, the path cost, is not a constant. Right? For example, in case of the Grassfire algorithm, the path cost was constant. Like if it moves from the current position uh, to 1 unit, it will only have a single uh, uh, cost, or a single unit of this path cost. And if it moves from here to here, again, the increment would be only a single unit of path cost. So like the path cost is essentially constant for Grassfire algorithm. Whereas in case of Dijkstra, it It's not a constant. For example, the cost of moving from a start node here to node 2 depicted here is 9 units, whereas the cost of moving from the start node here to node 6 is 14 units. So this path cost or edge cost is no longer constant for Dijkstra algorithm. So how do you find the most appropriate solution to reach from the start position to the goal position? It can go like this, it can go like this, it can go like this. There are multiple possible paths available. So how do you get to this most appropriate path? Actually, there are multiple ways. In according to Dijkstra algorithm, it basically starts by expanding all nodes similar to the breadth first search, except that the neighbors of the expanded nodes are placed in a heap and reordered subsequent to their costs. For example, if you are beginning with the start node, it will try to expand all the nodes, that is, expand all the neighboring nodes. So in the case of a start node, the neighboring nodes are node 2, node 6, and node 7. So it will expand through node 6, uh, node 2, node 6, and node 7. And what are the costs? So cost of reaching node 2 is 9 units. Cost of reaching node 6 is 14 units. And cost of reaching node 7 is 15 units. And the second part of the second point says uh, it's expanded and are placed in a heap and reordered according to their costs. So which of these nodes will be expanded further? So the nodes that will be expanded further will be the node that has the least cost. So out of these nodes, node 2, node 6, and node 7, node 2 has the least cost. So on the subsequent stage, node 2 will be expanded. And the neighboring node of node 2 would be node 3. And you would expand only node 2, right? For example, if I expand node 2, cost of traveling from node 2 to node 3 would be 24 units. So 24 plus 9 would be 33. See, now you have these three nodes, node 3, node 6, and node 7, out of which the node 6 have the least cost, which is 14 units. Then on the subsequent step, you will expand node 6, and it goes on and on. So at the end, subsequently, the cheapest state of the heap is extracted and expanded. This continues until the goal node is expanded. Solution can then be backtracked from the goal to start. So due to reordering the heap, time complexity may increase. So, like for example, once you expand a node, it each and every the next node to be expanded is based on this reordering. Reordering in the sense like which node has the least cost. So, like since we are doing this for each and every node expansion, the time complexity can really go up. So that is one thing about Dijkstra algorithm. We'll solve a few problems on Dijkstra algorithm to see how it basically works. And the third method of graph search algorithm is called A-star algorithm, where exactly you also have a cost. I'll reproduce this. Expected cost is sum of path cost and heuristic cost. So earlier we have, in the earlier cases, the heuristic costs were all zero. In case of Grasshopper algorithm, the path cost was constant. In case of Dijkstra, the path cost was not zero. And in case of A-star algorithm, the heuristic cost is also not zero in this case. So heuristic cost is basically taken as the distance of any cell from the goal in the absence of obstacle cell. For example, if you have an operational space, and if you have this has to be a start point, and if this is goal point, so the distance from its current position to the goal position, for example, consider it to be 5. that is considered to be the heuristic cost, right? The distance taken from any cell from the goal. So like if this is start, the distance from goal to start is heuristic cost. Or if your robot is somewhere around here, and if the distance from goal to this point would be 2 units, heuristic cost would be can be considered to be 2 units. So again, like just like Dijkstra, the heap is ordered according to the smallest cost value that includes heuristic function. Just like how we ordered the Dijkstra nodes based on which node has minimal cost function, we also do the same thing. But in this case, we also have the heuristic cost as non-zero. And all the other things are more or less essentially same as Dijkstra. The lowest cost node is extracted and expanded. This is continued until goal node is expanded, explode. And the lowest cost solution can be then backtracked from the goal through some sort of a backpropagation. So that is what A star is about. In this case, this heuristic cost is not zero. For example, this is one of these example that has been discussed on the lectures. So if you start from a start position, this is, I'll depict in a different color. So this is the start position. And over here, what you have is the goal position, right? And the path cost, g of x is the path cost. Path cost is nothing but the cost of movement from the start position to the node in study or node in observation. For example, if you're moving from here and if you want to go to this node, the path cost would be simply 1 unit because it only need to commute 1 unit downwards. So that is why this g of n is 1 unit. Whereas in the case of this node, it will have to take the path cost is 1.4 units because it will have to travel 1 power 4 units to the bottom left corner. 1.4 in the sense like you can, if you consider this to be a right angle triangle of units 1 and 1, this would be 1.4. This side would be 1.4. That is what this function g is about, that is path cost. And what about this heuristic cost? Heuristic cost is nothing but the distance from the goal position to this point, to this point in observation. So for example, if you consider this node is actually 2 units from the goal position. So that's why we have h as 2. And what about this one? So since this node is 3 units to the right of goal, so that's why we have h as 3. And what about this node? This node is actually 2.8 units away from goal position. Like, for example, if this is this node, it will be 1.4 units here and 1.4 units here. This is 1.4, this is 1.4. So the distance from goal to this node would be 1.4 plus 1.4, that is 2.8. And what about this node? So distance from goal to this node would be 1.4 plus 1.4 plus 1. That will be 3.8. So if you compute the path cost and the heuristic cost of each and every nodes, which of these cells will give you the least cost, that will contribute to the from the start position to the goal position. For example, if you expand all the nodes that are neighboring to the start node, you can basically estimate the path cost and the heuristic cost of all the neighboring nodes of start node, which are this node, this node, this, and this. And how do you propagate? So from start node, this node will have 2 plus 1.4, that is 3.4. And to your right, it will be 3 plus 1, that is 4. So ideally, it should move from the start position to here because this has the least amount of cost. least cost. I think I haven't made it complete. At the bottom, you have 2.8 plus 1.4, that is 4.2. And to your right, that will be 4.8. So out of all the neighboring nodes of the start node, this node has the least expected cost function. So ideally, it should start from here and it should go here. Then once it reaches here, then how can it go forward? It cannot go any further, right? Because there is an obstacle here. It cannot go any further. Then what will it do? It will try to reorder all the heaps so that the next node that you would possibly expand would be the node that has the least expected cost. So since this is next to an obstacle and since it cannot go any further, you can disregard this path. You can disregard this. And the next path, which has the least amount of expected cost, is 4.2. Because this has 4, it cannot also go here because it's actually a closed path. Then out of 4.8 and 4.2, 4.2 is the path which has the lowest expected cost. So once you do that, what will you do? You will basically uh, expand it further. You will expand the neighboring nodes of 4.2. So that is what this stage is. So the neighboring unexplored node of this node would be this node, this node, this node, and this node. And you can also compute the cost function g and the heuristic function similarly to what we have done. So like since this is already 1.4, since g is already 1.4, if you move 1 unit to your right, g would be 2.4. This would be 2.4. And again, if you move to here, it'll be g is 2.4. Again, you are moving 1 unit downward. And if you're moving diagonally, that will be plus 1.4. So like every movement lateral or longitudinal will add the path cost as 1. If you're moving diagonally, it will add to the path cost 1.4. So here G would be 1.4 is already there. Adding one more 1.4, it will be 2.8. And here also it will be G as 2.8. And what will be the expect heuristic cost? Maybe for this node, heuristic cost H would be distance from the goal position to this one. So that would be nothing but it can go 1.4 unit like this. Sorry, yeah, 1.4 unit like this and 1 unit like this. So that will be 2.4. 1 second. 2.4. And corresponding to this node, H would be, how much would be? It can go diagonally like this, 1.4, then 1 plus 1. That will be 3.4. So like once you have expanded all the nodes, once you have found out the edge cost and heuristic cost of all these nodes, all the neighboring nodes, you can again compute the total expected cost function. So in this case, it'll be 2.4 plus 2.4, that'll be 4.8. Here, this is 3.4 plus 2.8, that'll be 3.4. I guess it'll be 6.2, right? And here in this case, it'll be 3.8 plus 2.4. That'll be 6.2 again, I presume. And for this node, it will be 4.2 plus 2.8. That will be 7, I think. So again, which of these nodes have the least cost out of all these nodes? Again, if you consider this node has the least cost, total expected cost, right? So this node in the sense, this one actually 2.4 plus 2.4. Now what will you do? You will expand all the neighboring, unexplored neighboring nodes corresponding to this one. That will be this, this, and this. Because all the other, these are obstacles, these are already expanded. So since this has the least cost, you will expand all the neighboring nodes. So again, if you expand that neighboring nodes, then what are its costs? It will be 3.8 plus 1, that will be 4.8. And 3.44 plus 2 would be 5.4. 3.8 plus 3 would be 6.8. And out of this, which node has the lowest cost? It is this node, right? So you expand this further until you reach the goal position. And at the goal, the heuristic cost is 0 because distance from the goal point to its own location is essentially 0. So like now when you backtrack, which are the nodes that you have expanded? So you expanded this node, you expanded this node, then you expanded this node, and at the end you reach this node. So with that, uh, you can essentially backtrack to find the path that you can actually follow that will yield you the path with lowest expected cost. Because from start position, this is the node that you expanded. This was also another node you expanded. This was also another node you expanded, which has the minimum expected cost. And as a result, your robot can take this trajectory instead of any other way. So this trajectory or this path will yield you the lowest expected cost. So that is about A-star algorithm, where the heuristic cost is also involved. So the reason with the heuristic cost and this G is that like these are basically contradictory. Some may feel that you may want to go along a path which has a minimum path cost. Path cost is minimum path cost, like minimum effort with minimum effort, and H basically means the distance to the goal position. Sometimes yes, in some situations, the path with the minimum distance may not be the optimal path. For example, like if you want to go from a start position to a goal position, the minimal path is actually very rough, very harsh, and it's not very uh, suitable for you to commute. And there is also another alternative path that is a bit longer, but it's actually very smooth. And obviously, the shortest path will have this heuristic cost to be minimum. But the you have to pay more price. You have to pay more penalty. The path cost will be more for that. Whereas in the case of a longer and more smoother path, the path cost may be 0, but path cost may be a bit high, but heuristic cost will be lesser. So depending on how you tune your heuristic cost, there was a function epsilon. If you can recall that total expected cost f of n as g of n plus epsilon h of n. So depending on how you tune your heuristic cost, you can actually eliminate the unnecessary paths from the path planning algorithm. Because not always the shortest path is the most ideal path. Sometimes, if you take the longer and more smoother path, that could be even more beneficial. That could be even more of a reliable path. So, like depending upon how you tune your heuristic cost, you may get different solutions. You may get different paths actually. Okay, so that was about A-star algorithm, which was one of the graph search methods. So yeah, we have actually covered a straightforward approach. What we have covered until now was graph construction, where we discretize the map into a connectivity graph. This was one step, and once we have this connectivity graph, we do this graph search to obtain or to know which of this path would be the most ideal path or the optimal path. So another way of navigation or another way of path planning is what we call the potential field path planning. So this is entirely different to what we have covered so far. So like in this case, we treat a robot as a point, just like in the previous case. So this point robot will be under an influence of an artificial potential field. So this potential field is actually created by the start position, the goal position, and the obstacles all around it. So, due to this influence of this obstacle, the influence of this field due to this obstacle will actually try to create some sort of a repulsive force. Repulsive force. So, like when the robot is actually getting near to an obstacle, the field that is generated by this obstacle will push this robot away from the obstacle. And the goal position will have an attractive field. Like if you consider this as a sink and all others as source, the field, if you follow this contour lines, if you follow this quiver lines, it will basically, if it reaches here, it will try to move away from it. Or if the robot ends up here, it will also try to move away from it. And due to this influence of the field, it will try to drift away from the obstacle. And since the goal position is an attractive field, when the robot is near the vicinity of the goal, it will eventually converge into the goal position due to the influence of this artificial potential field. So, like there are multiple ways that you could model this thing. So, in essence, the robot moves by following this field. Like for example, like if you put a stone on a flowing river, you know how this stone will be carried, or a paper would be carried along the flowing river. It will be as per its field, how the flow is actually going. So the robot moves by following this field. The goal acts as an attractive force, and the obstacles acts as a repulsive force. And superposition of all the above forces are applied to the robot. So all the forces superposed on the robot, attractive and repulsive, coming from all sort of direction, that will determine the next trajectory or the next course of action of the robot. So like if the net force is still attractive, it will still go towards the goal. If the net force is still repulsive, or if the net force is still trying to move the robot away from the goal, it will move away from the goal. So it's more or less superposition of all the fields that is coming from that is coming due to the proximity of all the uh, proximity to all the obstacles as well as the goals. So that is about potential field path planning in essence, or in summary. Okay, so the next topic that we have discussed, like this is towards the end of week one lectures. So this is obstacle avoidance. So like again, under navigation, we have actually established, or there were actually two main objectives of navigation. So one was path planning. We have covered that so far. Like path planning included, graph construction, and graph search. All these things we have covered. Just a summary of all those topics we have covered. And the second objective of navigation is obstacle avoidance. Right? These were the two main objectives of navigation. So, obstacle avoidance is actually very important because, like, once the robot has planned the trajectory it wants to go, sometimes the objects may be dynamic. For example, if a human is actually walking through the field of robot, the obstacle may not have been previously registered on the map of the robot. It may come at a later point of time. So, like as the robot is moving, its sensor is constantly, sensing its environment. So, since it is actually sensing something, some foreign obstacle, it will have to modulate, or it will have to correct its trajectory so that it won't collide with this obstacle. So like it's actually a constant process. It's not like once you have decided on the trajectory, you only need to follow this trajectory. It's not the case. It will constantly it will have to constantly modulate its trajectory so that it won't get into any untoward circumstances. So, for example, the key point says the local obstacle avoidance focuses on changing the robot's trajectory as informed by its sensors during the robot's motion. So, like if the robot is actually moving through its planned trajectory, if it encounters an obstacle, it will have to navigate around this obstacle and continue its course of action. Right? So maybe this was this original path. This straight line was its original path. And somewhere in between, it encounters an unexpected obstacle. So it will have to navigate around this obstacle, then continue its usual course of action. So that phase is what this obstacle avoidance do. Okay, so this resulting motion is a function of robot's current sensor readings and its goal position and its relative location to the goal position. So like it has a start position, it also knows its goal position, and the resulting robot motion, like how it navigates around its obstacle, is actually a function of sensor readings, because only through the sensors can the robot detect this obstacle, and it should also know its goal position, so that it can actually circumnavigate around this obstacle and then depart towards its goal position. So like if it has no sense of its goal position, it will circumnavigate and maybe go to some random position, right? So that is why it says, the resulting robot motion is a function of sensor reading and goal position. It should be aware of its goal position also, apart from its sensor reading. Okay, so there are two major algorithms for path planning, two main algorithms that employ path planning. So like one of them is called, these are actually called bug algorithms, actually bug algorithm. And as you can see, there are two kinds of bug algorithms. So the basic idea is that the robot will follow the contour of the obstacle in the robot way and thus circumnavigate it. So for example, if this is a start point and if this is the goal position, this is what the robot has already planned. It has to take this path. But sometimes an obstacle may come in between. So what does it do? It will have to go along the planned trajectory. Once it encounters an object, it will have to circumnavigate around this obstacle and then depart. Once it has cleared this obstacle, it will depart for the goal along the pre-planned trajectory. And what is the difference between these two algorithms, bug one algorithm? So in bug one algorithm, the robot fully encircles the obstacle and departs from a point with the shortest distance to the goal. So what it is that it goes from the start location along its planned trajectory. Then it actually does, it fully encircles this obstacle. So once it fully encircles this obstacle, it will calculate the distance from each and every points of this path to this obstacle. And once it goes again through this path, it will actually depart towards this obstacle from a point which has uh, minimal distance from its location to the goal point. For example, if this point is of minimal distance to the goal position, it will depart from this point to here, right? Once more, it will go along the planned trajectory. It will circumnavigate. It will do a once full loop around this obstacle. Then from the point which has minimal distance, it will again depart towards the goal. And as you can see, this is not very efficient actually, because it does not need to, it's very unnecessary to loop this obstacle. It serves no purpose actually. So this is where this bug 2 algorithm comes. In bug 2, the robot starts to follow the obstacle's contour, but immediately departs when it can move directly towards the goal. So for example, if it goes along the planned trajectory and it cannot continue along this planned trajectory because there is an obstacle. So it will try to circumnavigate it, and once it has reached a point where it can directly move towards this goal, it will directly move. It does not have to wait until it reaches a point which has shortest distance. It can go from here. Once the goal is on its line of sight, it can directly depart. So that is the difference between bug 1 and bug 2. Bug 1 basically loops around it and departs from the minimal distance, whereas in the case of bug 2, it will circumnavigate until it reaches a point that can have a direct line of sight towards the goal, then it can depart. So that is what this thing is about, bug one and bug two algorithms, obstacle avoidance algorithms. In essence, as just as a summary. Okay, so since we have done with the summary of all the topics that we have covered during this lecture, we will basically solve probably a few sample problems that you can expect uh, for your weekly quizzes. Okay, so moving on to question one. Actually, these are fairly straightforward. Like if with whatever we have covered during this short session, we can easily answer all these topics. So the first question says, for a polygonal configuration space consisting of edges joining all pairs of vertices that can see each other, right? This above statement is suited for which path planning method? See, like for example, if we have a configuration space and if we have multiple obstacles, joining all the pairs of vertices, like these are the vertices. If we are joining all the pairs of vertices that can see each other, so this can see each other, use a different color, this can see each other. These two vertices can see each other, these two vertices can see each other. And this, as of now, these vertices cannot see anything else apart from its own vertices. So, like, what principle was this? Like, which of these methods is more suitable for this sentence? Which of these graph construction method? Like, these are all graph construction methods. And which of these graph construction method is most suitable for this statement? So, the obvious answer is like on its description, it is clearly obvious that option C is correct, visibility graph, right? And if there was a start position and there was a goal position, the start position and goal position are also vertices. So the start position can see this vertex, it can see this vertex, it can see this vertex, it can see this vertex. And the goal position can see this vertex, it can see this vertex, it can see this vertex, these vertex, all these things. And the shortest path would be somewhat like this. Would be somewhat like this from start to goal. And as you can see, the path actually moves as close as possible to the obstacles. So these were all defining features of visibility graph. So I hope that there is no further doubt or any conflict of interest in that regard. So the answer is indeed option C, visibility graph. And moving on, which of these following options come under graph search algorithms? So depth first, like at the beginning of this section, we have covered two topics relevant to graph search. Like one was graph construction, and the other one was graph search. So these were the subclassifications of path planning. And the question says which of the following comes under graph search algorithm. So depth first, that is graph search algorithm. Cell decomposition, if you can recall, this is a graph construction algorithm. Breadth first is also graph search algorithm. Visibility graph is graph construction. Voronoi diagram is also graph construction. So we have two correct answers. Depth first and breadth first are both graph search algorithms. So options A and C are indeed correct. So moving on to question 3. The heuristic cost of for all nodes in Dijkstra algorithm is equal to. So again, like we have considered three different cases of graph search algorithms. One was grass fire algorithm. The second was Dijkstra algorithm. The third one was A-star algorithm. And here the heuristic cost was 0. Heuristic cost was 0, but and path cost was constant. And in case of Dijkstra, again heuristic cost was 0, but path cost was not constant. Was not constant. And in case of Dykes A-star algorithm, heuristic cost was not equal to 0, and path cost was also not constant. So, like in essence, you can also say that this Dijkstra algorithm is a subset of A-star algorithm. If you consider the heuristic cost to be 0, A-star becomes Dijkstra algorithm. So the answer for this question is heuristic cost for all the nodes in Dijkstra algorithm is equal to 0 for Dijkstra algorithm. So that was the correct answer. Moving on to question 4. What are the statements that are true? So we'll go by one. The first statement says the potential field methods treats the robot as point under the influence of an artificial potential field. That is straightforward. That is indeed true. What about option B? The goal acts as a repulsive force and the obstacle acts as attractive force. So that is contradictory to just what we have discussed. So that is indeed false because goals acts as attractive forces and objects acts as repulsive forces. So in that regard, option 3 is indeed correct because this is exactly opposite to what we have seen in option B. And what about option D? Option D is the superposition of all the forces is applied to the robot, which in most cases is assumed to be a point in the configuration space. That is also true. We have just seen how this potential field method works. So in that regard, correct options are option A, C, and D. Yes. Okay, so moving on to question 5. It is asking for us to select the correct algorithm based on the figure that is depicted here. So this is essentially an obstacle avoidance algorithm. See, as you can see, the robot is from a start position. It goes, it encounters an obstacle, and as you can see, there are at least two loops in some parts. There is for sure there is a one complete loop going on around this obstacle. There is a one full loop going around this obstacle, and here also you can actually see at least one full loop, complete loop around the second obstacle. So the robot starts from here, it goes around a full loop, then again it comes back. And when it reaches at a point that has the minimal distance to the next obstacle, it will depart. Then it will encounter the second obstacle. It will do one full loop. Again, it goes. And once it reaches a point that has minimal distance to the goal, it departs. So based on that, you should know that this is a bug one algorithm because it basically does a one full loop or one full lap around each of these obstacles. So that is indeed bug one algorithm. Option B, that is question 5. Yeah, the correct answer is indeed bug one algorithm. And yeah, moving on to question 6. The below figure shows the start and goal positions for a robot to travel by avoiding obstacle polygons. The shortest path the robot will follow from its start position to the goal position using the visibility graph method is, so like as you know, we can actually establish multiple uh, connecting graphs. Connecting graph in the sense of the connecting the vertices that can see each other. So this would be one of them. Sorry. For example, this is one point. These points can see each other. Vertex 1 and 4 can see each other. Vertex 3 and 8 can see each other. Vertex 3 and 4 can see each other. Then 3 and 6 can see each other. 3 and 9 can each other. So on and so forth. And we don't have to complete it entirely, but based on intuition, it only asks you to find the shortest path. The robot will follow. So you also have limited questions. So which of these questions gives you the shortest path? So is it 15962? So this is 1. Then we have 5. Then we have 9. Then we have 6. Is it correct though? Because obviously the robot cannot move from 1 to 5 because it means that it'll have to go through this obstacle. So that is obviously not false. Well, obviously not true. That is false. Second option says 162. So this is 1. Then where is 6? 1 to 6, then 6 to 2. Is that also correct? 1, 6, 2. Again, that is also not correct because 1 to 6 means it again will have to go through this obstacle. So that is also not true. What about 1, 3, 6, 2? This is 1, this is 3, this is 6, this is 2. That seems feasible, right? I'll draw this. 1 to 3, 3 to 6, 6 to 2. This seems feasible actually. 1, 3, 6, 2. What about the final point? 1, 4, 12, 2. So this is 1, this is 4, this is 12, this is 2. What do you think is the path that has the shortest distance, shortest path? Obviously, it will have to be this path, right? This looks more or less like a triangle, right angle triangle. And if you consider this to be hypotenuse, obviously the hypotenuse will be shorter than sum of the other two sides. So obviously this path is actually shorter than this path. So in that regard, you can consider option C to be the correct answer for question 6. Yes. Okay, so moving on to question 7. This is actually a problem in Dijkstra algorithm because you have been given the cost of each of these nodes. So like if begins from node S, what is the cost of reaching node 2 is 2, and from 2 to 3 the cost of reaching is 24. So the cost of the edge cost also or the path cost for each of these nodes are actually given in the question. So with this data, what do you think would be the path that has the minimum cost, least cost? So the procedure is simple. You assign the cost for each node. The starting node has initial cost of 0. And at the beginning, each and every node has the expected cost as infinity. You can treat it as infinity. And just like a breadth first algorithm, you expand all the nodes, that is, all the neighboring nodes corresponding to all the neighboring nodes to the starting node S. So what are the neighboring nodes starting to S? The neighboring nodes are 2, 6, and 7. So if you go along this path, the cost to reach 2 would be 10. And since 10 is actually less than infinity, you can replace this infinity by 10. Because that is what the definition of Dijkstra says. Like you have to reorder the heap based on the minimal cost. And if you go along this path, to 6, the cost is 24, which is also less than infinity. So that will be 24. And if you go along this path, the cost of expansion is 12. That is 12. So you have actually expanded all the nodes you have actually expanded all the nodes coming from the node S. So you can actually block this node away. I'll use this highlighter just to let you know that this node has been fully expanded. Now, if you consider all the other nodes, all the other unexpanded nodes, node 2 has a cost of 10, node 6 has cost of 24, node 7 has a cost of 12, and all the other unexplored nodes have cost of infinity. Then the next possible node that you would want to expand would be node 2, which has the least cost. Because you have to, every time you have to reorder and expand. So the node that has the least cost is node 2, and then you have to expand node 2. And the neighboring node of node 2 is node 3. Node 2 only has a single neighboring node, which is node 3. And if you expand along node 3, the cost will be 10 plus 24, that will be 34. That will be 34. Okay, so you have expanded node 2 as well. There is nothing else to be expanded in node 2. So I'll also cover node 2 as well, because that also has been already fully expanded. Then what are the remaining nodes that is unexpanded? We have node 3, which has a cost of 34. We have node 6, which has a cost of 24. And node 7, which has a cost of 12. So since node 7 has the least cost, expected cost, we will expand node 7. So if you go along this path, it will be 12 plus 5, that is 17. 17 is less than 24. So we can go along this path. So if I replace this 24, we can replace it by 17. So we have covered this path. And if you expand node 7, so it's the second neighboring path along node towards node 5. That will be 12 plus 13, that will be 25. So you can replace this infinity by 25. So you have covered this node as well. Then if you expand node 7 along node T, that will be 44, 12 plus 44, that will be 56. So you can replace this infinity by 56. So now you have expanded node 7 as well. So you can also cover it off node 7. Yeah, node 7, you can also be covered as well. Then now which node has the least cost? We have 17 over here, we have 25 over here, we have 34, we have 56. So since 17 is the node which has the least cost, we can expand node 6. So if you expand along this towards 3, 17 plus 18 would be 35, right? 35. So 35 is actually greater than 34. So you don't have to replace 34 with a higher value. So you can consider this to be expanded because you can't go along that way. If you expand it along this way, that'll be 17 plus 21. That'll be obviously greater than 25. So you don't have to replace 25 again. And if you expand 6 along 6 along this will be 17 plus 5. That'll be obviously greater than 12. So again, you don't have to expand again along 7 as well. 6 to 7, you don't have to expand it as well. So in essence, you have also covered node 6. This is also, node 6 has also been covered. Now, which of the nodes have the least cost? We have 25 over here. We have infinity here, 34 and 56. Then we can expand along node 5. Node 5 to further unexpanded nodes. So if you expand it along here, this will be 25 plus 2. That will be 27, which is less than 34. Right? So you can replace this 34 by 27. We have considered this path. And if you expand 25, expand along towards node 4, this will be 25 plus 15. That will be 40, 40. So this has also been covered. Then again, if you expand node 5 to node 6, 25 plus 18 would be 43. That will be less than 56. So you can replace this 56 by 43. This also has been covered. So we have expanded all the, we have expanded node 5 as well. So you can block it off. Node 5 can also be blocked off. Now, the remaining nodes, out of the remaining nodes, the least cost corresponds to node 27. Sorry, node 3, which is 27. So how will you expand? If you expand node 3 along node 4, this will be 27 plus 6. That will be 33. That is obviously less than 40. So you can cross off this 40 to be 33. So this path has been expanded. And if you expand node 3 towards T, that will be 27 plus 90. That will be greater than 43. Right? 27 plus 19 will be obviously greater than, that will be 46. That's greater than 43. So you cannot expand along that node. So yeah, I think we have also covered node 3 as well. So node 3 is also fully expanded. I can cover this off as well. Now, which of the nodes has minimal cost? Now, node 4 has minimal cost, which is 33. So if you expand along this node, 33 plus 21, that will again be greater than 43. So you cannot also cover that as well. So again, node 2 has been fully expanded. You can cover this off as well. So now what you have to do is that you have to backtrack. You have to backtrack from the goal position T along this path, the path that gives you 43 as the total cost function, right? So which of these path will give you the cost as 43? You have to backtrack from the goal position. So I think it was here. I think this was the correct answer. T, then it will go to 5, then it will go to 7, then it will go to S. This path actually gave you 43, I suppose, because this path is 12 plus 13 plus 18, right? 12 plus 13, 25 plus 18, 25, 35, that is 43. Right. So once you have found out the minimum value of the goal position, minimum cost of this goal position, like earlier it was infinity, through some point it was 56. Finally, we have converged it to 43 when all the nodes have been covered. So we have to backtrack. So which of these paths will give you the cost as 43? So that is the correct answer, shortest path. So in that regard, 12 plus 13 plus 18 gave you 43, and that path corresponds to S75T, and hence your correct option is option E, S75T. Right? So I hope there is no further questions on that. Option E is indeed the correct answer. The correct path is This one. Okay, so moving on to question 8. Which graph search algorithm is used in Graphfire algorithm? So if you can recall, Graphfire, we started from a start position, and then we expanded all the neighboring nodes, 1, 1, 1, 1, which are adjacent. Then we expanded all the nodes, 2, 2, 2, 2, right, like that. So which algorithm corresponds to this? Is it depth first? Is it cell decomposition? Cell decomposition is a graph construction algorithm. It has nothing to do with the graph search algorithm. Visibility graph and Voronoi diagram are also graph construction algorithms. So you can directly eliminate these options. So is it depth first, breadth first, or Dijkstra? So like based on how it propagates, it's obviously breadth first actually. Breadth first algorithm. Because it expands one node, then it will expand its neighboring node. Again, it expands its neighboring node. That is what breadth first algorithm was in principle. So yeah, the correct option is indeed option C, breadth first. Yeah, the correct option is breadth first for Graphfire algorithm. That is an example of Graphfire breadth first algorithm. Okay, moving on to question 9. It's a lengthy sentence, so some of them have to fit onto this film on this blank. So what does it say? So it says this algorithm expands the node starting from the from the start, similar to breadth first search. So it's similar to breadth first search, except that the neighbors of one expanded nodes are placed in heap and reordered according to their value, which corresponds to the cost. So this could either mean A star or Dijkstra, because this reordering of this heap happens in either A star or Dijkstra. Okay, subsequently, the cheapest state on the heap, the top element after reordering, is extracted and expanded. This process continues until the goal node is expanded or no more nodes remain on the heap. A solution can then be backtracked from the goal to the start. So this applies to both A star and Dijkstra, except the heuristic cost of A star is not zero. Not zero heuristic cost. Whereas in the case of Dijkstra, it has zero heuristic cost. And since this question says nothing about the heuristic cost, we can assume it to be zero because it says nothing about heuristic cost. So in that regard, the correct answer is indeed Dijkstra algorithm, option F, right? Because depth first algorithm is actually not similar to breadth first. So like the question itself is similar to breadth first. So you can eliminate this immediately. Cell decomposition is a graph construction method, so you can eliminate that. A star is a potential candidate. Graphfire algorithm is actually an example for breadth first algorithm, but it does not deal with reordering of the heap based on the cost. Then we have bug algorithm that was essentially a collision avoidance algorithm that has nothing to do with this question. You can eliminate that. So the only remaining options are Dijkstra and A star, out of which Dijkstra fits here the most. Yeah, so the option is indeed F. Option is F, but it's not breadth first, it's indeed Dijkstra. Yeah, maybe there was a mistake in this answer key, but option F is indeed the correct answer. Yeah. Moving on to question 10. Which of the graph construction method matches with the following sentence? The robot's path comes as close as possible to the obstacles resulting optimal paths are minimal length solutions. So like we have seen this multiple times in this very session. It is actually a defining property of visibility graph, where the obstacle comes as close as possible to the robot comes as close as possible to the obstacles. So that is indeed the correct answer. Visibility graph, yes. Moving on to question 11. The concept of dash for a polynomial configuration space consists of edges joining odd pairs of vertex that can see each other, including both initial and goal position as vertices as well. Okay, so again, this is also a defining property of visibility graph, because like we have seen this on previous occasions in the preceding slides also. So the connectivity graph is actually created by connecting all the vertices that can see each other. So that is also again a defining property of visibility graph. So yeah, in that regard, the correct answer is indeed option uh, yeah, option E, visibility graph. Yes. Moving on to question 12. Yeah, it's a statement. It says it has given a statement and the question is followed by the statement. Well, we'll see the statement what it is first. The goal of path planning is to find the best path in the map's connectivity graph between the start and goal, where the best refers to the selected optimization criteria, for example, shortest path. And the expected cost is given as f of n is g of n times epsilon h of n. F of n is expected cost, g of n is path cost, and h of n is heuristic cost. Which of the path planning algorithm where the heuristic cost is not zero? So in case of Dijkstra, we know for a fact that it is zero. In case of A star, this is not zero. In case of Grassfire, it is zero. In case of Dijkstra and A star, it's zero for Dijkstra and it's not zero for A star. Grassfire and Dijkstra, it is zero for both. So non-zero heuristic cost is only a thing for A star algorithm. So in that regard, option B is indeed correct, A star. Moving on to question 13. So this is also about a graph search question. So dash search expands the node up to the deepest level of the graph until the node has no more successors. The search backtracks by expanding the next neighboring node of the start node until its deepest level, and so on. So again, like we have seen this exact definition before on one of the previous slides. So this is also again a defining feature of depth first algorithm, because it will the expansion goes on to a deepest level until there are no more adjacent nodes, then it will backtrack and again it propagates through a different branch till it reaches its deepest level. So this goes on until it reaches the goal position. So that is indeed a feature of depth first algorithm. Yeah, depth first. That is indeed the correct answer. So moving on, question 14. Like this is also similar to what we have seen. This is also similar to this Dijkstra algorithm. But I will leave you to solve this problem because we have already solved a similar problem. And I'll give you the final answer. The most optimal path would be to go from uh, it's actually S uh, yeah, the S23. Yeah, this would be the optimal path. S25381. So from S, then 2, then 3, then 5. Sorry, I think I messed it up. It's from S, starting from S, then it goes to 2, then it goes to 5, then it comes back to 3, then 8, then 1. So the total cost would be 2 plus 1 plus 1 plus 1. So 2 plus 1, 3 plus 1, 4, 5, 6. Right. So once you go through this path, your final cost of this position T should be 6. And the path that would give you the cost function 6 would be this one. You can try this on your own, right? Because it's the procedure we have discussed with the problem on one of the previous questions, actually. So this is indeed the correct answer. And if you want, you can try it on your own. And if you still are not able to solve this, you can reach me back on the discussion forum. I can assist you if you are not getting this answer. So the correct answer is indeed option A. Okay, a couple more questions. For question 5, choose the wrong statement. Question 15. So the first statement is Dijkstra algorithm is a special case of A-star algorithm where the heuristic cost is 0 for all costs. So that is indeed true because f of n, the expected cost is path cost plus epsilon times heuristic cost. In case of Dijkstra, this heuristic cost is 0, but in case of A star, h of n is 0, but in case of A star, h of n is not 0. So first option is indeed a correct statement. I'll not take a check mark. We want to find the wrong statement. So this is true. Second statement says potential field path planning treats the robot as a point under influence of artificial potential field. The goal acts as repulsive force and the obstacles acts as attractive force. So this is false because goals acts as attractive and obstacles acts as repulsive. What is being stated here is exactly the opposite. Okay, so option 3, since Voronoi diagram graph construction method maximizes the difference to the obstacles, any short range sensor on the robot will be in danger of failing to sense its surroundings. So that is also true because Voronoi keeps the robot as far as possible away from all these obstacles. But if it is using a short range sensor, it may not be able to detect the obstacles or surroundings. So eventually it may fail if the distance between the obstacles are actually too large. Okay, the final option says in Bug2 algorithm, the robot fully circles the object first, then departs from a point with the shortest distance towards the goal. So that is also false because but it is Bug1 algorithm that fully encircles the obstacle, then departs along the shortest distance. Bug2 never fully encircles. Like it only contours the obstacle, but once it has a line of sight towards the goal, it will immediately depart. So that is also false. So the question asks you to select the wrong statement, and option B and option D are wrong. So the correct answer to the question is option B and option D. Okay, so this is question 15. Okay, so yeah, this is the right answer. And this is also correct actually, because this statement is also false. But in the answer key, you have been only given option 2. Yeah, but typically when you in your exam, if you feel like multiple answers are correct, you have to select multiple answers. Otherwise, you may not, you may lose marks. So in this case, both of these answers are correct. You have to select both of these answers because both of them are correct. Correct answers for this question. Okay, so moving on to question 6. Choose the correct algorithm in the following figure below. So like we have solved a similar question earlier. This solves an obstacle avoidance problem. So there is the robot actually moves towards an obstacle. So once it detects an obstacle, it'll try to encircle, or it will try to contour this obstacle. And once it has reached a sufficient point, it will depart to this next obstacle. And once it has reached the next point, it will again further reach. Nowhere in this graph you can see it fully encircling the obstacle. Nowhere in the graph it's fully encircling. So out of bug one or bug two, it should be fairly obvious that bug two algorithm would be the correct choice. Because the correct answer can only be bug one or bug two. All the others are either Graphware is actually a graph search algorithm. All the other options are all the other options are graph search. And for this question, only bug one or bug two applies. And since the robot does not fully encircle the obstacle, it is obviously bug two algorithm. So that is indeed the correct answer. Okay, so yeah, this is about it. This will be the end of today's session. I do not have anything further to add. We have summarized the topics that we have covered during the session. We have also seen some sample questions. So, yeah, now that we have reached this end of the session, I don't have anything further to add. Unless you have any more questions, I shall wind up the session.
Hello, sir.
Hello.
Sir, I am having a doubt regarding the week 4 problem, sir.
Week 4, okay. What was the problem? What was the doubt?
Sir, it is about the inertia inertia problem that you were given for the assignment. Actually, they were asking the answers in Newton. Uh, Actually, just a unit mistake, sir. Newton by
Oh,
Newton meter, sir. So, but there is no conversion of kg to Newton, sir. Can I send the problem, sir?
kg to Newton. Yeah, you can. What was the question? Because I don't know the question for
Uh,
assignment of 4.
Sir, I have sent in the chat. I have sent, sir.
In the chat. Okay. Okay, I'm going through it right now. Uh, okay, consider a robotic system having a mechanical gyroscope which reads the following. Okay, solution range is given as 1.3 to 1.32. So what was the question actually? What was the concern?
Sir, actually, they are asking the value of answer in Newton meter, sir.
Yes.
But they are not converting the kg into Newton, sir. Is it the correct way, or you want to modify, sir?
Yeah, because kilograms you have to multiply it with 9.81 to give to get you this mass, right? Torque, units of torque is anyway Newton meters, right?
Yes, sir. If you multiply by 9.81, it becomes like 12.91 something, sir.
Sorry. But why do you really have to multiply it with 9.81? Because if you can see the solution range, mass is given as 5 kilograms. So the moment of inertia would be mk square, right? Radius of gyration is also given.
Yes, sir.
So
But we are not converting the mass is given in the kg, sir. We are not converting into Newton.
Why do you have to convert it into Newton? You
Because
don't
they
have to.
ask Newton, sir. Newton meter, sir. They are asking the torque as.
Okay, so like you see, actually, it's the unit is I omega, right? I is kilogram meter square. What you
Yes,
have
sir.
is I kilogram meter square, and omega's unit is rad per second. Rad per second actually. So kilogram meter. Can you see my screen? Is it
No, no, sir. It's not visible.
okay? Okay. 1 second. It's automatically converted to Newton. That was what I was telling actually.
So we do not need a separate multiplication for converting.
No. I'll try to explain this to you. 1 second. Uh, yeah. So I would be mk square, right? So a moment of inertia is mass times radius of gyration square. So unit of mass is kilogram, and unit of k square is meter square, right? And torque is I multiplied by omega. So kilogram meter square multiplied by omega is unit of omega is radian per second. So if you rewrite this, it will be kilogram meter. Uh, is it I omega omega p? There is also one more omega p, right? I omega omega p. So
Yes,
like
sir.
you have,
Omega.
yeah. So again, one more radian per second will be there. So if you rewrite this, it'll be kilogram meter per second square. Then you also have one more meter here. Then you also have a rad square, which does not have any unit. So this kilogram meter per second square itself is Newton, right? And remaining is 1 meter actually. So units are automatically taken into account,
Oh,
right?
okay, sir.
So that is how you get
Yes, sir.
Newton meters actually, because everything is already there in the pro. You don't have to convert it or anything like that.
Okay, sir.
Yeah.
Sir, and another doubt regarding the fourth week is that actually you said that for wait, I know. Can I send another screenshot, sir, for asking
Yeah,
the doubt?
sure. No problem.
Hello.
Yeah. What was the question about?
Sir, it is about the sensor system which can be classified as both extroceptive and active sensor system, sir.
Okay.
But you thought that the answer is only gyroscope, but they also provided with the additional two answer. So we want to consider that also the answer, or in the exam point of view, we just consider gyroscope. That is my question.
Up I have to see the question. Can you send it? I don't know the question.
Yes, sir, I can. Sir. Yes, sir, I have sent you.
Okay. Yeah. Okay.
And this is the second question, sir.
How are you getting these PDFs? Where are you getting these PDFs actually?
Actually, it is provided by the NPTEL website, sir. After
One
1 week,
second.
they automatically upload the answers. Sir.
Okay. So let me check. Which question was it?
It is the second question, sir.
Okay. The second question. Select. Okay. Select the sensor uh, which cannot be classified as exteroceptive and active sensor. So contact switches Contact switches is not an active sensor,
Yes, sir.
but it is an exteroceptive sensor, I think.
But the question is both exteroceptive and active sensors. So
Which cannot be, which cannot be. So it cannot be exteroceptive, it cannot be active. So it has to be proprioceptive. It has to be proprioceptive and it has to be passive also.
okay, sir.
So yeah, this thing is contact switches cannot be proprioceptive, right? Contact switches is still exteroceptive. So that solution is not correct.
Sir, my question is that, sir, we want to use this problem solving session as the answer. Actually, you have given the answer as gyroscope, sir. Gyroscope only is the correct answer. Actually, it is also the correct answer, but they have given like this the three answer they have selected and also reduced the mark for the assignment. So I am asking that if the same question is in the NPTEL exam, then what is the correct answer, sir?
Okay, so maybe there was a mistake in this LPTL. So we'll do one thing. We'll withdraw that question so that marks won't be lost.
Okay, sir.
You know, because we can treat the question itself as wrong, then we can see if something can be done. If that
And
was
that is also the same case in the first question also, sir. You have thought that the remotely operated mobile robot are more has least complexity and but it is also considered as a
uh, which of this question? Question one.
first question, sir.
Have you raised this on the discussion forum?
Sir, I don't know where that is. I
No, because
don't have any idea, sir.
on the discussion forum, then it will be easier for people to correct it actually. Which of the below constrained system is constrained to perform tasks having least complexity? Yeah, that is correct only, right? Autonomous underwater robot is least complexity actually.
But there is also a remotely operated mobile robot, sir. It is more
Re-
least complex.
Remotely
Uh,
operated in the sense like if the task
the
is
gra-
slightly complex, then we need human intervention, right? So like if
yes,
the
sir.
task is very complex, too complex, then human himself I will have to do. So as the complexity keeps on increasing,
Yes, sir.
then you can make the robot to do its own,
Yes, sir.
right? Yeah. So perform least complexity would be something having more degree of autonomy can do tasks that has lower and lower complexity actually. So I think option that is correct, I think. But have I ever discussed anything similar in my session? I'm not sure.
Actually, you have discussed that in the graph it is stated that remotely operated robots are much more least complexity.
Let me check that in remotely operated. Is that so?
Yes, sir.
In the graph, in the live session, is that so?
Yes.
So in the if I can recall the graph, remote operation is used for in a task that is more complex, not least complex.
Okay, sir.
Yeah, you have to revisit. Should I share my screen? Is it visible?
No, sir.
Okay, 1 second. 1 second. Yeah, see, right? So here, task complexity is high,
Okay,
and
sir.
this is where remote operation is actually. So yeah, remote operation is mostly used for tasks that are high complex. And the autonomous robots, maybe underwater robot or anything, wheeled robot, which has least task complexity, is used for is also highly autonomous, but it is also used for tasks having lower complexity.
Sir, they also asking for the least sensing also, sir. In the question they have fully stated that system have least sensing and
Least
perception
sensing.
capability. Yes, sir.
Yeah. but it has some level of autonomy, I believe. So that's why it
Okay.
says autonomy, I think. That's why it says autonomy. Yeah, the question itself is not very least sensing. I think it should mean at least, I think, at least sensing and perception capabilities, not least. Yeah, but anyway, that question itself is confusing. Maybe that question also can be retracted, I think.
Okay.
Yeah, so which are the questions? So questions one and
Question 2.
question two. Okay, questions one and question two. Okay, so yeah, maybe I'll probably forward this to NPTEL team to withdraw that or maybe consider for reevaluation or something.
Okay, sir. Thank you, sir.
Okay, thank you. So yeah, with that I'll close this session, right? Thank
Okay,
you.
sir.
Thank you. Bye.